Ever feel like time just slips through your fingers? Like it's this constant, steady thing for everyone.
Yeah, that's our everyday experience, right?
Well,
But it turns out the universe plays by slightly different rules.
exactly. Welcome, everyone, to Cosmic Origins Revealed. Today, we're taking a really deep dive into something, well, mind-bending.
We're talking about how speed, incredibly high speed, can actually mess with time itself.
Right. We know you're listening because you're curious. You want to understand these big ideas without, getting buried in complex math.
And that's our goal today. We're unpacking time dilation and what happens when you get close to the speed of light.
It's one of those concepts from Einstein that really challenges how we think time works. Our intuition says tick-tock, same for everyone.
But relativity shows us that when extreme speeds get involved, things change dramatically.
So let's jump right in. The absolute core idea from special relativity. What is it, fundamentally?
Fundamentally, it's this. The faster you move through space, the slower you move through time.
Slower through time. It sounds like something straight out of sci-fi.
It really does, but it's actual physics. Think about the Large Hadron Collider at CERN, the LHC.
Okay, yeah. Where they smash particles together at incredible speeds.
Incredible is the word. Those protons, they get accelerated to 99.9999999% of the speed of light, just shy of the limit.
Wow. Okay, so what happens to time for those protons?
Well, their clocks effectively tick much, much slower than ours. But there's something else, too, related to space.
Go on.
From the proton's perspective, that huge 27-kilometer ring they're racing around, it actually shrinks.
Shrinks. How much?
Down to about 4 meters.
4 meters. 27 kilometers. That's astonishing.
It is. It's called length contraction. It goes hand in hand with time dilation at these, relativistic speeds. Distance itself changes for the moving object.
Okay, let's take that idea bigger, like interstellar travel, say, to Andromeda.
Right, our nearest big galactic neighbor.
Yeah.
Billions of light years away, a vast distance.
So if we had a hypothetical ship that could get really close to light speed,
From the perspective of the astronauts inside that ship, that enormous distance to Andromeda would shrink massively due to length contraction.
journey wouldn't feel like millions of years to them.
Not at all. Theoretically, if they got close enough to light speed, they could cross that gulf in maybe just minutes of their own time.
Minutes to cross millions of light years. Okay, my brain is officially bent.
Yeah, it does that. But here comes the really wild part, the counterintuitive bit.
The catch.
The catch, time dilation. Imagine they make that trip, seems like minutes to them, maybe they turn around and come straight back, also minutes for them.
Okay.
They arrive back on Earth, and millions of years would have passed on Earth.
Millions. While they only experienced maybe hours or days.
Exactly. They'd return to a future they couldn't possibly recognize. Friends, family, civilization, all gone, replaced by whatever millions of years brings.
So you could explore the galaxy quickly from your perspective.
But you couldn't really come back and share it in any meaningful human timescale. It's a profound consequence.
Right. Okay, maybe we can unpack why this happens. You mentioned a thought experiment. The light clock.
Ah, yes, the light clock. It's a beautifully simple way to visualize it. Imagine two mirrors, okay, parallel. And you have a beam of light bouncing straight up and down between them. Each bounce up and down is one tick of this clock.
Simple enough. Like a very basic timer.
Precisely. Now, imagine this clock is moving past you at a very high speed, say, sideways.
Okay.
From your perspective, watching it go by, does the light still travel straight up and down?
No, I guess not. If the clock is moving sideways, the light would have to travel diagonally to catch up with the moving mirror.
Exactly. It travels a longer diagonal path for each tick.
Ah, okay. Longer path.
But, and this is the absolute key, the foundation of relativity. The speed of light is constant for everyone, for you watching and for someone moving with the clock.
Right, the universal speed limit.
So, if the light travels a longer path in the moving clock, but its speed hasn't changed, what must happen to the time it takes for one tick?
Must take longer.
Bingo. Each tick takes longer from your stationary perspective. The moving clock appears to run slow.
Wow. A simple clock shows why time slows down with motion.
It captures the essence of time dilation perfectly.
And Einstein apparently had this kind of insight thinking about a streetcar.
Yeah, the story goes he was imagining chasing a beam of light, or maybe riding alongside it. He realized if you could travel at the speed of light,
What would happen?
from your perspective, the light beam would be stationary next to you. Its waves would be frozen. Time, for you, would essentially stop.
Time stops at light speed.
From your frame of reference, yes. But for someone standing still, watching you zoom by at light speed, their time would tick along just fine.
That difference, that relativity of time depending on motion, that's the core of it.
That's the core of special relativity. It wasn't just pulled out of thin air, though. There was a conflict in physics at the time.
Between which ideas?
Well, you had Newton's laws. Good, solid mechanics. They said velocities or relative speed depends on your viewpoint.
Okay, makes sense. My speed in a car is different relative to the road versus relative to another car.
Exactly. But then you had Maxwell's equations for electricity and magnetism. Amazing work. And they predicted the speed of light.
And the problem was?
Maxwell's equations implied the speed of light was constant. The same value, no matter how fast the source of the light was moving or how fast the observer was moving.
So Newton says speeds are relative. Maxwell says light speed is absolute. They can't both be right.
That was the puzzle. Einstein's genius was realizing they could both be right, but only if you abandon the idea of absolute time.
So instead of relative speeds, we get relative time.
Precisely. Time itself has to stretch or shrink, depending on your motion, to keep the speed of light constant for everyone.
He had another thought experiment for this too, right? With lightning in a train.
Yes, another brilliant one to explain why simultaneity, whether two things happen at the same time, is also relative.
Okay, lay it out for us.
Imagine a long train moving fast. And imagine two lightning bolts strike the very front and the very back of the train simultaneously.
Okay, simultaneous strikes. How do we know they're simultaneous?
Let's say there's an observer standing on the ground exactly halfway between where the strikes hit. Light from both strikes reaches them at the exact same moment. So for them, definitely simultaneous.
Makes sense.
Now picture someone on the train, also sitting exactly in the middle, but the train is moving forward.
Right, so they're moving towards the light from the front strike.
And away from the light from the rear strike. Exactly. So which light pulse reaches them first?
The one from the front, because they're moving towards it.
Correct. So for the person on the train, the front strike happened before the rear strike. They were not simultaneous.
Even though the person on the ground saw them as simultaneous.
Yes. Whether events are simultaneous depends on your frame of reference, your state of motion. It's another direct consequence of light speed being constant and leads straight back to time being relative.
It all connects. And this led Einstein to think about space and time being linked. Spacetime.
That's the next step, yeah. General relativity builds on this. He realized space and time aren't separate backdrops. They're woven together into a single four-dimensional fabric. Space-time.
Like a trampoline sheet, sort of?
That's a common analogy, yeah. And massive objects like planets, stars, they warp or curve this space-time fabric around them.
And that warping is gravity.
Warping is gravity. It's not a force pulling things, according to Einstein. It's objects following the curves in space-time caused by mass and energy. Mind-blowing, really.
It really is. And, it's easy to think of this as purely theoretical, happening out near black holes or whatever, but it affects us here, right?
Oh, absolutely. It's not just theory. It has real, measurable effects we rely on. Think GPS.
The navigation in our phones and cars, how does relativity affect that?
Well, GPS relies on a network of satellites orbiting Earth, each with a super precise atomic clock on board. Now, those satellites are moving very fast, maybe 14,000 kilometers per hour. So special relativity says their clocks should tick slightly slower than clocks on Earth. Time dilation due to speed.
Right, like the moving light clock.
Exactly. But there's also general relativity. The satellites are farther from Earth's gravitational pull than we are.
Less gravity up there.
Right. And general relativity predicts that clocks tick faster in weaker gravity.
So one effect slows the clocks down, the other speeds them up.
Correct. The gravitational effect is actually stronger than the speed effect for GPS satellites. The net result is that the satellite clocks run faster than ground clocks by about 38 microseconds, or 38,000 nanoseconds per day.
That sounds tiny. Does it really matter?
Hugely. If the GPS system didn't constantly correct for this relativistic time difference, your position would drift off by kilometers every single day.
Kilometers. Wow. So GPS literally wouldn't work without accounting for Einstein's relativity.
Not accurately, no. It's a daily proof that time dilation and gravitational effects on time are real. We use it every time we navigate. Pretty cool verification for Cosmic Origins Revealed listeners, huh?
Definitely cool. Okay, let's go back to that spaceship approaching light speed. What would things look like? You mentioned optical effects.
Yeah, things would look weird. First, there's aberration of light. Stars ahead wouldn't seem stationary. Their apparent position would shift forward due to your motion relative to the incoming light.
Like the stars are being pushed aside.
Sort of, yeah. And then there's the Doppler effect, like with sound waves, but for light.
Blue shift and red shift.
Exactly. Light from stars ahead would be compressed, shifted to higher frequencies, blue shifted, making the sky in front seem brighter and bluer and also kind of contracted.
And behind.
The opposite. Light waves would be stretched out, shifted to lower frequencies, red shifted. The view behind would seem dimmer, redder, and expanded.
So it's like you're flying into a bright, compressed cone of light with darkness expanding behind you.
That's a pretty good picture, yes. Initially, you might think these are just visual illusions, tricks of light.
But they reflect something deeper happening.
Yes, they tie back into the real physical effects, especially time dilation, which we keep coming back to here on Cosmic Origins Revealed.
Because as you speed up, your path through space-time changes compared to someone stationary.
Precisely. Your trajectory through that four-dimensional fabric is different, and the amount of time you experience along your path is less than the time experienced by someone standing still. It's a real difference in elapsed time.
And that length contraction we talk about with the LHC tunnel, that's real too.
Oh, yes. Very real from the traveler's perspective. The length of objects or even the distance to a star in the direction of motion actually shrinks.
So the distance to Andromeda really becomes shorter for the astronaut.
For them, yes. That's what makes traversing those vast distances seem plausible in terms of their own experienced time and perceived distance.
Okay, but how would, say, a sphere look as it flew past you at near light speed? Would it just look squashed?
Good question. Length contraction implies it would be squashed into a sort of pancake shape in the direction of motion, but visually it's more complex.
How so?
Because light from different parts of the sphere reaches your eye at slightly different times, especially from the back versus the front of the moving sphere. This can lead to an effect called Terrell-Penrose rotation.
Rotation, so that it wouldn't look just squashed.
It might actually appear rotated or strangely distorted rather than just flattened. The sphere might still look spherical, oddly enough, but rotated. It depends on the viewing angle and how you account for the light travel time. It gets complicated visually.
Physics is rarely simple visually at those speeds, it seems.
Definitely not intuitive. But the underlying principles, time dilation, length contraction, are the core physical effects.
And underpinning all of this is the absolute speed limit, right?
The ultimate cosmic speed limit. Nothing with mass can reach or exceed the speed of light in a vacuum, period.
No matter how much energy you pump into accelerating it.
Nope. As you get closer and closer, it takes more and more energy to gain even tiny increments of speed. Reaching SIA would require infinite energy for anything with mass.
So even if you're on a ship constantly firing its engines, accelerating forever.
From your perspective on the ship, if you shine a flashlight forward, that beam of light will still race away from you at speed. You never catch up. You never even lessen the gap in terms of relative speed to the light itself.
Light always wins. It's a fundamental constant. We keep seeing that on Cosmic Origins Revealed.
It's the bedrock, which leads people to think about loopholes.
Like WarpDrive. Star Trek stuff.
Exactly. The idea there isn't to travel through space faster than light, because you can't. The idea is to warp space-time around the ship.
How would that work?
Theoretically, you'd need to create a bubble, contract space-time drastically in front of the ship, and expand it massively behind the ship.
So the ship itself isn't moving fast in the bubble, but the bubble moves through space-time.
That's the concept. The bubble rides a wave of distorted space-time, potentially covering vast distances much faster than light could in normal flat space.
That's great. Can we build one?
Well, there's the rub. The physics, as we currently understand it, suggests you'd need something called exotic matter, or matter with negative mass energy density.
Negative mass. Does that even exist?
We've never observed it.
Yeah.
All known matter has positive mass energy. So, while mathematically interesting, warp drives require physics we don't have and materials we've never seen. It's highly speculative for now.
So, back to reality for Cosmic Origins Revealed. No FTL travel through space.
Not by breaking cis, no. But the consequences of approaching cis time dilation length contraction, those are absolutely real.
And they profoundly change how we have to think about space, time, and exploring the universe.
Completely. They open up possibilities for reaching distant stars within a human lifetime for the traveler, but they also create that incredible disconnect in time with wherever they left.
So, wrapping up our deep dive today, the big takeaway.
The faster you move through space, the slower time flows for you relative to a stationary observer. It's not intuition, it's physics.
Beautifully shown by particle accelerators, and the core idea behind any realistic dreams of interstellar travel, with all its weird temporal baggage.
Exactly. We've really peeled back the layers on how relativity reveals time isn't this fixed universal metronome we assume it is, it's flexible.
It really is. So the final thought we want to leave you with today, pondering this on Cosmic Origins Revealed.
If time isn't absolute, if it stretches and shrinks depending on speed and gravity, how does that change our view of everything?
Yeah, how does it alter our understanding of the universe's own vast history? Billions of years. Did time flow differently in the early universe?
And looking forward, what does it truly mean for humanity's future among the stars, knowing these relativistic rules are in play?
Lots to think about. It's definitely one of the most fascinating aspects of our cosmos. Keep pondering.